Hello and welcome to another video of From Concept to Circuit. In this video, we are going to continue our journey to make a network analyzer using ADALM Pluto. In the last video, part one of this video, we showed the network analyzer we made that was able to measure S21 and S11 using ADALM Pluto. For S11, we are using an RF bridge that you can see in this video. Here, I have two of these RF bridges that I bought. Both of these are a very cheap RF bridge. They are in the range of $10 to $15. And their promise is they operate from zero point 0.1 to 3,000 megahertz range. So we are going to see how in this frequency span, how they operate, what is their quality, and we are going to see in the network analyzer that we made how we first calibrate S11 and then how after calibration what would be the performance of the network analyzer. So please tune in. We are going to explore the beautiful concepts beyond measuring RF frequency, voltages, and waves. Before moving on to measurements, I just want to review RF bridge and concept behind it one more time to get a better background. I talked about it in the previous video, part one of network analyzer, but I just wanted to give a very brief review here as well. So basically, I mentioned in part one to find the reflection or any reflected wave that is needed to measure S11, we can either use a directional coupler, which is in many cases, especially in higher frequencies, they have a higher quality compared to this resistive bridge. Or we can use a resistive bridge to save a little bit on the budget, um, as these resistive bridges use resistors which can be used as surface mounted resistors that have very low parasitics, and therefore we can implement a relatively cheap and a wideband um, RF bridge to help us to measure any reflection. The way they work is they create a bridge. You can assume we have these four resistors. For now, assume that R1 and R2 are just fixed resistors, for instance, 50 ohm. Then we also fix our Rref, which is our reference R, to be 50 ohm again. And we want to measure um, our device under test using this resistive divider. Basically, we connect our device under test between these ports, one being ground, the other one is the input of the RDUT. What happens is that uh, if we uh, if we convert this differential voltage at the R resistor bridge and we call it V out, we can end up with this equation based on the input voltage that shows us VO is equal to RDUT over R1 minus Rref over R2 uh, as the numerator, and the denominator is 1 plus R dut R1 multiplied by 1 plus R ref R2. You can see here that this VO, assuming that our R ref is equal to R1 and R2, essentially uh, uh, will be uh, will be proportional to R dut and a VB. And basically, you can see VO becomes 0 when R dut over R1 becomes equal to Rref over R2. And assuming R1, R2, Rf are all equal to 50 ohm, basically VO becomes 0 when R dut becomes 50 ohm. This can be used as a probing point for us to measure whatever reflection we have from our device under test, and that reflection can be used to measure S11, right? So the way we do is that we have this RF bridge and then we connect be out to the receiver, the second channel receiver port of our ADALM Pluto. The input, which is the we need VB to simulate this resistor bridge, is connected to our transmitter. Okay, so this is the concept behind this resistive bridge. And what you can see, there is one issue here. One is the voltage that represents the reflection is differential. Here in this diagram, an amplifier is used to make this a single-ended voltage. However, especially when we go at higher frequencies, let's say we want to measure this reflection at 3 gigahertz, having an amplifier that can operate in this very wide band region can be challenging. So one other thing is that we can use some uh, uh, balloons, which are basically some RF devices that can be used to convert the differential to single-ended for us. You can assume they act as a transformer, and because there are some companies that can provide discrete transformers that can operate at higher frequencies, and we can go and just buy those. Uh, this becomes very interesting because we can just go buy a balloon that is designed with high qualities. The core of the transformer has very high quality, and the parasitics of this is low. Therefore, we can use it to achieve a transformation at higher RF frequencies. We definitely in future videos, because this balloon is used in many places in RF design, even when when we are in integrated circuit. Uh, we are going to touch in detail the concept behind the balloon. But for now, because our focus for this video is just implementing the network analyzer and seeing it uh, in effect when it's working, uh, we just finished the conversation here, and we'll go over more details about the balloon in the future videos. But you can see if we use a balloon, the transformer that can be used to convert the differential to single-ended, because the secondary port is isolated from the primary port, so therefore one of the ports of the secondary can be connected to ground. We can convert this differential to single-ended. These bridges, you can make it yourself in this website. Actually, someone tried to make their own RF bridge using this diagram, but you can also go and buy these RF bridges. For instance, this is one of the RF bridges that are available in the market with very low prices. And here, this is our balloon that using some ferrite bits, uh, the core of you can say it's not fully a transformer, but you can say it's used to create a very high inductance here. So we are going to use this RF bridge and another RF bridge that I showed earlier in the beginning of the video in our spectrum analyzer to measure reflection. What we do is we connect the reference to a 50 ohm resistor. The other side, which is the input, is connected to our transmitter, and the DUT is going to get connected to the device that we want to measure its S11. Then the output of this RF bridge is connected to the second channel of our ADALM Pluto that is used to measure whatever voltage we see here, and and then based on the voltage we can measure the reflection. Before moving on, just one last thing I want to mention is that you can define something called directivity, basically to uh, quantify the non-idealities of this RF bridge. Basically what you want is you want to see, okay, I have this port that gives me the amount of mismatch for the resistance. But this port itself is not ideal. It doesn't have characteristic impedance of 50 ohm all over the working band. It's claimed here that this is working from zero point 0.1 to 3000 megahertz, but we're going to see this in action that this is not the case. And what's happening is that assuming that I terminate the output port of this to 50 ohm, what I want to see here is that all of the wave, if it comes here, is absorbed. None of it gets reflected back. That's the directivity. Basically, there is no leakage back to the main device from for the reflection voltage. We don't have any leakage back. There is no wave coming back from this port. However, this is not the case because of definitely the parasitics here. There is and other non-idealities. So some of the waves that represents the reflection of the DUT when comes here and wants to go to the ADALM Pluto, some of it gets reflected back. And this reflection, which is in this case, you can say it's a leakage, it causes some inaccuracy in the measurement in some frequency for us. Um, you will see at some frequencies when we connect DUT to 50 ohm, actually the voltage we see here becomes larger compared when here is open. Because when we connect DUT to an ideal 50 ohm, we based on this, we would expect the voltage here to be zero and definitely be lower than the case that here is open. But there are, due to some non-idealities, the parasitics here, sometimes the leakage wave becomes very large, and you won't see that. You actually see that when you connect at that those inaccurate frequencies, when you connect the 50 ohm here, the uh, the wave you see at the output of this port becomes larger compared when it's open. And this definitely depends on the implementation of our balloon and our reflector. Uh, Definitely these are not ideal. The parasitics here are not ideal, and we will have some crossovers. So we have two RF bridges actually, and we are going to see which one behaves better in this scenario. And you will see the one that has circular uh, transformers or inductors basically behaves better in many frequencies compared to here, to this RF bridge. So now let's move to the measurements. Now let's look at the code and also the setup. The assumption for this video is that you have already watched the videos. We talked about how to make a spectrum analyzer and also a frequency analyzer that earlier I made, which are basically talking about how we can measure the amplitude from the receiver first, like how we can transmit the tone, and the receiver, how we can measure the amplitude difference, and by averaging and applying a low pass filter, remove noise and get a higher quality amplitude. We talked about those on those videos, and I put the descriptions down. I put the links down to the in the description. But I just want to show the configurations that I defined on top of the code here. First, we defined the rejection we want out of the low pass filter, the cutoff frequency, the transition width of the filter. Then we define the number of measurement steps we want to do in the frequency sweep, or the number of calibration points we want to do. Also, there are some smoothing filter that their constances are added here, which are basically to smooth the plotted S11 or S21 data. Uh, Also, then the sampling frequency, the number of samples we take each time, the tone of the transmitter, and also the minimum and maximum frequency in the sweep. One thing to note is that this is the case even for like all the spectrum analyzers or the network analyzer. In order to reduce the noise and improve the resolution, either resolution in the frequency or the uh, amplitude measurement, which is basically lowering down the noise floor, uh, the main step is to increase the number of averaging. That means that we need to take more points for each read. We need to increase, this is if we increase the number of points, we have more points. So when we are doing the averaging or the filtering, we can apply a, a better filter. Uh, Also for the frequency axis, if we want to improve the frequency steps, we can increase the number of steps. But these means that um, for higher resolutions, we need to spend more time to get the measurement. And these are definitely depend on the measurements we want to do. So now you can see the setup. Basically here we have the transmitter connected to the RF bridge, and the output of the RF bridge via an attenuator is connected to the second RX channel of the ADALM Pluto. This is the other RF bridge that we are going to see its frequency response. Uh, but basically, this is the way we calibrate for S11. The device under test should be connected here. The device that we want to measure is S11. But now for calibration, I have terminated this to a 50 ohm termination because the initial step for calibration is connecting a 50 ohm here. So this is the way that the calibration is done. Basically, what calibration does is you can see from the TX we have this cable that has some loss. There we have this PCB for RF bridge that has its own uh, non-idealities. Then coming out is another cable and another attenuator. And basically, what we want to do in calibration, we want to make the measurements relative, meaning that we basically by comparing open calibration results with terminated calibration results, we basically uh, remove the effect of these cables or other inaccuracies from our measurements. So let me run the code here. Okay, so this is our window. We can change the start and stop and number of steps, and also start the calibration for S11. So basically what we do is we just hit the cal S11 and it asks us now connect the 50 ohm load, then okay. So now because the load is already connected, we just press OK. And after it measures the received amplitude for 500 points for 50 ohm load, then it pops up another window saying that now connect a open um, load, connect an open load, which basically we remove this, then press OK. So this may take some time because I'm trying to gather some like 500 points to just show the frequency response of the two RF bridges we have here and here. I call this a circular because it has circular uh, cores, and this one is straight. But I will let the calibration run for these two, and I just want to show the comparison of the S11s we take from these ones. So now I just press OK, and it starts calibration. Now let's look at the output results. The Python code has this feature that exports the data that is measured during calibration to a spreadsheet. So we can use this spreadsheet to see how are the results, and basically based on the results, we can see how well is the RF bridge is behaving. And actually, we are seeing very interesting results in this spreadsheet. So this is not the default spreadsheet because the default spreadsheet only has these three columns, which basically for each frequency shows what's the amplitude that's measured when load or 50 ohm was connected or when open was connected. But I added the second data set, which is for the circular RF bridge to this spreadsheet to just show you the comparison of these two RF bridges. So the left one is the straight RF bridge, and the right data set is for the circular. You can see, for instance, here, and this is the plot for the straight RF bridge. Basically, I plotted these open and load versus each frequency. You can see here several interesting things. One is, for instance, at low frequencies, you see, especially when the load was connected, I'm seeing very noisy data. And also, for instance, let's say at 0.24 gigahertz, the load was showing minus 30 dB and open was showing minus 22 dB. This means that if I want to make the open to be equal to zero, because what calibration does after this point is that say, okay, this is open. If the calibration is applied, I just want to make this zero, because when the open is connected, I have all the voltage reflected back. So this is zero, and therefore it's just that it makes the other one when the load is connected to minus 10 dB. Just offset this, right? But you can see then the dynamic range I can get with this RF bridge is like in order of 10 dB or so. Plus, one other issue that I talked earlier in the video is the directivity of the balloon um, is um, is not definitely ideal, and sometimes you can measure the the, um, the amplitude when the load is connected to be higher than the open due to some of the leakage that is getting back to from the RF output port to the bridge, right? So, and you can see actually for the straight RF bridge, this is happening at around 1 gigahertz and then 1.5, meaning that if this is the open, the amplitude that is measured when calibrating with open load, the open amplitude becomes much smaller compared to the load, right? And this is not something we want. So showing that this RF bridge is not um, acting good in this frequency region. With some degrees, we can use this region and this region, um, and definitely not the crossing points, because in the crossing point, we cannot differentiate between the open and load. Um, Therefore, especially at these crossing frequencies, we cannot use this RF bridge. At much higher frequencies, above 3 or 4 gigahertz, also you can see very bad behavior from the RF bridge. Now, if we look at the circular RF bridge results, which is the second plot here, you see a much better behavior from this circular RF bridge. You can see the load. When the load is connected, you can see it in the blue plot and the open in the red. You can see from point 0.1 to around 2 gigahertz, the load is much smaller than the open, giving us a good dynamic range and also good accuracy when you use this bridge. So this bridge is acting much better. If we didn't have this crossover around 2 to 2.4, we could use it. We could even see much wider range, because even after this crossover, it's still behaving very good up to 3.8 gigahertz here, right? Our ADALM Pluto by default, because we are extending the frequency range of the ADALM Pluto, the IC is guaranteeing performance from zero point 0.3 to 3 gigahertz, but we are using it up to 6 gigahertz, so we cannot for sure rely on the lower or much higher frequency ranges. But actually, we are going to in future videos, we are going to uh, acquire an even higher quality, uh, uh, either a directional coupler or a higher quality RF reach, to try to push to 6 gigahertz region, so from 0.1 to 6 gigahertz regions. But you can see, except for these crossing frequencies, we basically have a very good, we can get a very good dynamic range and accuracy using this circular RF bridge. One other thing that I added to the Python code is just when the calibration is done, and we want to apply it, basically we check for this crossing point. If the open and load get very close to each other, their value, we we know that this is not the region we have good accuracy to operate in. So basically, we try to avoid these points as we are measuring the S11 after the calibration data is up. So now I'm going to use this circular RF bridge connected, and for one last time, just show you how now S11 behaves when I connect and disconnect load after the calibration done. And we will end this video. Uh, these two videos cover the basics of how we can make this network analyzer, how the code is implemented, how the calibration is being done, and also some demos. But from this point, we are going to use this device in the future videos to do more measurements of different uh, devices that we want to measure, their S11 and S21. And also we are going to use even directional couplers or higher quality RF bridges. For those I'm actually thinking of making one RF bridge ourselves, because not to try to compete with any commercial product, but the reason even I'm trying to make this network analyzer or a spectrum analyzer is basically to show the concept behind these measuring devices and how we can make a cheaper version of them at home. Um, and from these concepts, we can gain very good insight on what's going on in the background when we are using these devices, right? Commercial network analyzers, if we say not a vector network analyzer which measures the phase, but the network analyzer which is the amplitude, are just maybe um, uh, they are more accurate in the frequency, the PLL frequency they make in the transmitter or the receiver. It's much less noisier. The directional coupler they use or the RF bridge they use is much higher quality, or the overall front end of the receiver or the uh, transmitter is less noisier, right? So these are the things that separate us from achieving very standard or high quality measurements. But nonetheless, with even using an ADALM Pluto, you can see we can go and measure S11 or S21 up to 3.8 gigahertz with this RF bridge, which is only $15, uh, dollars, which shows that the idea or concepts behind these are not very complicated. Okay, so now let's just go and look for the final demo, which is when the calibrated data is applied. Now I have started the app after the calibration. As you can see, I have connected the circular RF bridge because it was showing better performance when we were looking at the S11 calibration results. So I'm using that, and I set the minimum start frequency to be 100 meg and the stop to be 3 gig, although the circular bridge showed that it can be pushed to a little higher frequencies, but for now I just set it to be around 3 gig. And you can see now that the DUT is open, nothing is connected here. The S11 that we are measuring is around -1 to 0 dB after the calibration data is applied. Please ignore the S21 for now because I have not connected the S21 to the first RX channel, because for this video we just focused on S11, how the calibration works and how it behaves. Now what I'm going to do is I will connect the load, the 50 ohm termination load, back to the DUT. You can see as soon as I connect the load, S11 drops to -30 dB. This -30 dB, as I showed in the calibration results we were looking earlier, definitely the dynamic range changes for this RF bridge, because this RF bridge doesn't have a flat frequency response over the frequency span. So the dynamic range changes. For instance, here we are measuring -30, and the other place we are measuring -40. But one thing is that during that band, we can be sure that somehow the dynamic range of around 20 to 30 dB is guaranteed, and we can use that. Although in the future videos, we definitely will explore more uh, uh, directional couplers with higher qualities, so that the directional couplers that show much better flatness over the frequency, and also the directional couplers that do not have any crossover frequencies. But nonetheless, this app, when we apply the calibration, we we check if there are the points of any crossover where the open and short get close to each other, meaning that we cannot rely on that data. So we skip that point and a few points in its vicinity, because we know that whatever we measure there and apply the calibration will not show correct results. Yeah, so you can see this is the S11. Uh, as I mentioned, we can definitely change the sweeping range, the number of steps, or change the number of points that we take. But one thing is that depending on the accuracy we want and depending on the uh, noise performance or the frequency resolution, we can change those parameters. Yeah, there you have it. We are looking at the working network analyzer using ADALM Pluto. Definitely for now, the limitation for us is the RF bridge. We definitely need to use a better RF bridge or use a quality directional coupler, which we are going to do in the future videos. But still, even the reason I wanted to start with RF bridge was showing that still with a cheap RF bridge, we can make a high frequency network analyzer at home. Although the Pluto itself, it's a pricey device, but uh, we can use it to make the network analyzer. Definitely, once we go and make a directional coupler or buy a directional coupler, we will have a much better performance. There you have it. I hope you enjoyed this video. Please share this video and subscribe, and comment down below if you have any suggestions or feedback for checking the performance of the network analyzer, and also if you have any idea how to improve the performance. I have, as I mentioned in part one, I have already uploaded the code on GitHub, so please go and take a look.